A question meant to disturb your intuition. In a universe filled with stars, galaxies, and distances so vast they defy imagination, astronomy relies on a unit that almost no star actually occupies, a distance that marks no boundary, a number that does not correspond to anything you can point to in space. It is called the parsec. You will find it everywhere in professional astronomy, in star catalogues, in research papers, in the equations that describe the structure and expansion of the universe. It sounds authoritative, precise, unquestionable. But here is the problem. Nothing special happens at 1 parsec. Stars do not change behavior. Physics does not shift. Space does not care. The universe gives no indication that this distance matters at all. That should make you uneasy, because in science, units usually emerge from nature. A second is tied to atomic vibrations. A meter is tied to the speed of light. Even a light year, enormous as it is, makes intuitive sense. It connects distance to time, motion to scale. The parsec does none of this. It is not based on time, it is not based on energy, it is not based on any physical property of the universe. So why does nearly all of modern astronomy depend on it? The answer is unsettling. The parsec exists not because it describes the universe well, but because for most of human history we were blind to depth itself. For thousands of years, humanity could map the sky, but not measure its distance. The stars formed a perfect unmoving backdrop, a flat dome with no depth, no scale, no way to know how far anything truly was. And when that finally changed, when humans at last cracked the problem of stellar distance, the method we used permanently shaped how we measure the cosmos. The parsec is the scar left behind by that breakthrough. To understand it, we have to return to a time when the universe had no depth at all. For most of human history, the universe was flat. Not physically flat, but perceptually flat. The stars appeared nailed to the sky, locked in perfect patterns that never changed. Night after night, century after century. The constellations held their shapes with eerie precision. This was not ignorance, it was evidence. Ancient astronomers measured star positions with astonishing care. They tracked their motions, catalogued their brightness, mapped the heavens in detail, and every observation told the same story. The stars did not move relative to one another. If something does not move, you cannot measure its distance. Your brain understands depth only because of motion and perspective. Your two eyes see the world from slightly different positions. That tiny difference is enough to judge distance. Take that away, and the world collapses into a flat image. That is exactly what the sky looked like. To ancient observers, the stars formed a rigid shell surrounding Earth, a celestial sphere, solid, eternal, unchanging. The planets moved against this background, wandering through the constellations, but the stars themselves remained fixed. This idea endured for nearly 2,000 years because nothing contradicted it. Even when telescopes were invented, the problem did not go away. Telescopes revealed mountains on the moon, moons around Jupiter, and countless faint stars invisible to the naked eye. But they did not reveal depth. The stars still refused to shift. Astronomers knew Earth was moving. They knew it orbited the Sun. And that created a terrifying implication. If Earth moves through space, nearby stars should appear to shift against distant ones over the course of a year. This effect, called parallax, should be unavoidable. But it wasn't seen. Year after year, astronomers searched for it and found nothing. No shift, no wobble, no depth. There were only two possibilities. Either Earth was not moving, or the stars were so unimaginably distant that even Earth's vast orbit was too small to reveal their position. The second option was far more disturbing. It meant the universe was vastly larger than anyone had imagined, distances so enormous they escaped all intuition, scales so extreme that human perception simply failed, and yet, without proof, it remained speculation. Parallax became astronomy's most dangerous question. Solve it, and the universe would suddenly gain depth. Fail, and the cosmos would remain an unknowable dome. For centuries, no one succeeded. The stars held their secret, until human instruments became precise enough to notice something smaller than vision itself. a shift so tiny it bordered on the impossible, and when that shift was finally detected, it did more than reveal stellar distances. It forced astronomers to redefine how distance itself would be measured forever. The idea was simple. If Earth moves around the Sun, then our viewpoint changes. Nearby stars should appear to shift slightly against the background of more distant ones. Measure that shift, use geometry, and distance reveals itself. On paper, it was elegant. In reality, it was nearly impossible. The shift astronomers were searching for was smaller than 1 arcsecond, an angle so tiny that it defied the limits of human perception, smaller than the blur caused by Earth's atmosphere, smaller than the flexing of metal as temperatures changed, smaller than the vibrations caused by wind, footsteps, even a beating heart. Early telescopes were not built for this kind of precision. Their mounts flexed, their lenses warped, their alignment drifted over the course of a night. Every attempt to measure parallax drowned in noise. Still, astronomers tried. Some thought they had succeeded. They published results claiming to have measured stellar distances at last. But when others repeated the observations, the results did not agree. The claimed distances varied wildly. The stars seemed closer one year, farther the next. Something was wrong. One of the most famous failures came from a brilliant experimenter who believed he had finally seen the long-sought shift. What he actually detected was something else entirely. Not parallax, but the effect of Earth's motion combined with the finite speed of light. This phenomenon caused all stars to appear displaced in the same direction, mimicking motion without revealing distance. It was real, it was measurable, and it was misleading. Other astronomers tried different strategies. Some observed pairs of stars, hoping one might be closer than the other. Others tracked the same stars for decades, searching for slow changes. None succeeded. But these failures were not wasted. They revealed something unexpected. Some stars were not fixed at all. Over long periods, a few drifted across the sky, not from parallax, but from their own motion through space. This discovery hinted at a shocking truth. The stars were not embedded in a rigid sphere. They were independent objects, scattered through vast distances, moving freely through space. The universe was not a shell, it was a volume. By the early 19th century, astronomers understood the problem clearly. Measuring stellar distance was not conceptually difficult, it was technically brutal. The angle existed, but it was buried beneath layers of error. Solving it would require something unprecedented, not just better instruments, but a new obsession with precision itself. And that obsession was about to arrive. The breakthrough did not come from a new theory. It came from a refusal to accept error. By the early 19th century, astronomers understood the problem with painful clarity. The universe was not hiding parallax. Human instruments were burying it. Every telescope, every mount, every observation introduced distortions larger than the signal itself. Solving the problem would require a different kind of astronomer. Not one chasing discovery, but one obsessed with precision. Friedrich Wilhelm Bessel did not begin his career studying the stars. He trained as a clerk, taught himself mathematics at night, and approached astronomy as a discipline of calculation and error control. Where others saw observations, Bessel saw uncertainty. And uncertainty was something he intended to defeat. He did not trust his telescope. He measured how its metal expanded and contracted with temperature. He tracked how gravity flexed its structure depending on where it pointed. He studied how air bent starlight differently on warm nights and cold ones, dry nights and humid ones. Nothing was ignored. Even Earth itself was a problem. Its motion introduced aberration. Its axis slowly shifted. Its orbit was not perfectly circular. Every one of these effects was larger than the parallax he was trying to measure. So Bessel modeled them. Night after night, he observed the same star again and again, not to look for a single dramatic shift, but to build a pattern, a cycle, a motion that repeated as Earth moved around the Sun. He chose his target carefully, a faint star with an unusually fast drift across the sky. Not parallax, but real motion, a clue that it might be nearby. For over a year, he measured angles so small they bordered on the absurd, fractions of a second, each measurement useless on its own, powerful only when combined. When the analysis was finished, something emerged from the noise, not a guess, not a suggestion, but a repeating geometric signal. The star traced a tiny ellipse against the background sky, a motion that matched exactly what Earth's orbit demanded. For the first time in history, the distance to a star had been measured. The universe had depth, but the method used to reveal it carried consequences no one yet understood. Because in solving the problem of distance, Bessel had unknowingly created a unit that would outlive him. A distance defined not by space itself, but by the angle humanity was finally able to see, and that distance would soon be given a name. Bessel had measured an angle, nothing more, a shift so small it barely existed, traced over months as Earth moved around the Sun. On its own, the angle meant nothing, but geometry gave it power. Draw a triangle. One side is Earth's orbit. The distant star sits at the far point. The tiny angle at Earth tells you how long the other side must be. No assumptions about stars, no guesses about brightness, just pure geometry. For the first time, distance emerged directly from measurement, but the number Bessel obtained was enormous. Tens of trillions of kilometers, hundreds of thousands of times farther than the Sun. Writing these distances was awkward. Calculating with them was worse. So astronomers did something subtle. They stopped asking how far the star was in kilometers. Instead, they asked a different question. At what distance would Earth's orbit appear to shift by exactly 1 arcsecond? That distance was fixed, defined, and it came directly from the geometry of parallax itself. If a star showed a parallax of 1 arcsecond, it sat at that distance. If the parallax was smaller, the star was farther. Half the angle meant twice the distance. A tenth of the angle meant 10 times farther. The arithmetic became effortless. Distance equaled 1 divided by the measured angle. No tables, no conversions, no guesswork. They gave this distance a name, the parsec, a contraction of parallax and arcsecond. Here is the unsettling truth. The parsec was not chosen because it represented anything special in space. It was chosen because humans happened to measure angles using arcseconds, a system inherited from ancient civilizations that divided circles for convenience, not physics. Had humanity chosen a different angular system thousands of years earlier, the parsec would not exist. And yet, it worked. For astronomers processing hundreds of measurements by hand, this unit was transformative. Errors became obvious, patterns emerged, distances could be compared instantly. What began as a mathematical convenience quickly became habit, then convention, then infrastructure. Catalogues listed distances in parsecs. Equations assumed them, students learned them, software encoded them. No committee voted, no authority declared it law. The parsec spread because it was useful, and once it spread far enough, turning back was no longer possible. The universe had gained depth, but it had also acquired a ruler that was quietly, profoundly human. Once distance could be measured, the universe did not gently expand. It exploded. The first stellar distances were shocking. Even the nearest stars lay trillions of kilometers away. The Sun was no longer near the edge of anything. It was adrift in a vast, empty volume. And as more parallaxes were measured, a pattern emerged. Stars were not arranged on a shell. They were scattered. Depth piled on depth. Distances multiplied. What once felt unimaginably far became merely nearby by cosmic standards. The parsec followed this expansion effortlessly. A few parsecs for the nearest stars, hundreds for clusters, thousands for the structure of the Milky Way itself. Astronomers simply added prefixes, kiloparsecs. The center of our galaxy lay thousands of parsecs away. Spiral arms stretched across tens of thousands more. The Milky Way was no longer a small system of lights. It was a vast rotating disk embedded in space. Then came a deeper shock. Fuzzy spiral nebulae filled photographic plates. For decades, no one knew what they were. Clouds within our galaxy, or something far beyond it. When their distances were finally measured, the answer was staggering. They were not inside the Milky Way. They were galaxies, each one containing billions of stars. And the parsec stretched again. Megaparsecs now described reality. millions of parsecs between islands of stars drifting in darkness. The universe was not just large, it was structured. Clusters of galaxies formed vast webs. Empty voids spanned distances beyond comprehension. The parsec scaled effortlessly upward, quietly keeping pace with revelation after revelation. And then something stranger appeared. The farther away a galaxy was, the faster it seemed to be moving away. Distance itself was tied to motion. Space was expanding. This discovery reshaped cosmology, but the equations describing it were written in the same unit born from parallax. Kilometers per second per megaparsec. A unit derived from a tiny angle now governed the fate of the cosmos. The parsec had escaped its origin. What began as a convenient ruler for nearby stars had become the backbone of cosmic scale. The universe grew beyond imagination, and the parsec grew with it. By every reasonable standard, the parsec should have disappeared. Once astronomers understood the true scale of the universe, better units existed. Kilometers were precise, light years were intuitive, time and distance merged into a single elegant idea. A light year told a story. The parsec did not. It required geometry, angles, arcseconds, diagrams, explanation layered on explanation. Even professional astronomers admitted it was unintuitive, and yet it refused to go away. The reason was not tradition, it was dependency. Every distance method beyond parallax was calibrated using parallax, Cepheid variables, supernovae, entire galaxies. Each rung of the distance ladder inherited the unit from the rung below it. Change the unit at the bottom and everything above it fractured. Equations were written in parsecs. Catalogues stored parsecs. Software assumed parsecs. Generations of astronomers learned to think in parsecs. Switching units now would not be a translation, it would be a reconstruction. Even worse, the parsec made mistakes visible. A parallax of half an arcsecond meant 2 parsecs, an obvious result. A parallax of 1/10 meant 10 parsecs. Instantly recognizable, using other units buried intuition beneath conversion factors. For working astronomers processing thousands of measurements, this mattered. Convenience hardened into necessity. By the 20th century, the parsec was no longer just useful. It was structural. And then came the age of data. Astronomy shifted from individual observers to massive surveys. Millions, then billions of stars. Databases were built. Pipelines automated. Assumptions locked in. Distances were parsecs by default. To change that would require rewriting software, reprocessing catalogues, retraining intuition across an entire field. No single astronomer could justify that cost. So the parsec remained, not because it was perfect, but because everything depended on it. A unit born from human limitation had become a load-bearing pillar of modern science, and tearing it out now risked collapsing the structure it held together. As the parsec became permanent inside astronomy, something strange happened outside it. The public learned the universe in a completely different language. When space exploration captured global attention, the distances were not given in parsecs. They were given in light years. News articles, documentaries, textbooks, and planetariums all chose the same unit. Because light years made sense. They carried meaning without explanation. Light is fast. A year is familiar. A light year instantly tells you that you are looking into the past. 4 light years means 4 years of travel at the universe's ultimate speed. The parsec offered none of that. To explain it, you needed diagrams, geometry, angular measurements inherited from ancient civilizations. Even after explanation, it felt abstract. So a quiet divide formed. Professional astronomers spoke in parsecs. Everyone else spoke in light years. The same star would have 2 distances depending on the audience. A research paper described it as 1.3 parsecs away. A documentary described it as 4.2 light years. Both were correct. But they told different stories. Light years emphasized time. They made distance emotional. You were seeing ancient light, history crossing space. Parsecs emphasized measurement. They connected directly to how the distance was obtained. No poetry, just structure. This split became permanent. Students encountered it early. Popular books taught light years. University courses switched to parsecs. Reading real research required learning a new numerical intuition. Many never crossed that gap. Those who did entered a different universe, one where distances were not felt but calculated, where intuition came from geometry rather than imagination, and then a mission launched that ensured the divide would not close anytime soon, a spacecraft designed to measure parallax on an unprecedented scale. Its data would define astronomy for decades, and it would speak only one language: the language of the parsec. The spacecraft did not look dramatic. No towering rockets, no distant worlds in its sights. Its mission was quieter, colder, and far more ambitious. It would measure angles, not arcseconds, not even fractions of arcseconds, but shifts so small they bordered on the meaningless. Motions smaller than a human hair seen from thousands of kilometers away. This was the Gaia mission. Its goal was simple in description and staggering in execution: measure the positions and distances of more than 1 billion stars. To do this, Gaia watched the sky endlessly. As it slowly rotated, stars drifted across its detectors again and again. Each pass refined their position. Each year added another layer of precision. Gaia did not guess distances. It measured parallax directly. And parallax speaks only one language: arcseconds in, parsecs out. Every star Gaia measured came with a parallax value. Every distance was derived by inverting that angle. No interpretation, no storytelling, just geometry repeated at unimaginable scale. The result was a 3-dimensional map of the Milky Way, unlike anything humanity had ever possessed. Stars were no longer points. They were coordinates, positions, velocities, histories. Entire branches of astronomy were rewritten overnight. Stellar evolution, galactic structure, exoplanet science, all recalibrated using Gaia's distances, and every one of those distances was in parsecs. By sheer weight of data, the parsec became unavoidable. Too much software assumed it. Too many catalogues depended on it. Too many discoveries were built upon it. Changing units now would mean rebuilding astronomy itself. The parsec was no longer just tradition, it was infrastructure. A unit born from a barely detectable angle now underpinned humanity's most precise map of the cosmos. The universe had never been measured so well, and it had never been described so completely in a language so few outside the field truly understood. By the time humanity could finally see the universe in 3 dimensions, the damage was already done. Not damage in the sense of failure, but impermanence. The parsec had outlived the problem that created it. It began as a workaround, a clever response to a nearly impossible measurement, a way to turn a vanishingly small angle into something usable, something stable, something repeatable. But once the universe revealed its depth, the parsec did not step aside. It stayed, because science is not rebuilt from scratch each time understanding improves. It grows by layering. Each new discovery rests on the structures beneath it. Units become assumptions. Assumptions become infrastructure. The parsec became one of those foundations. Today, astronomers know it is arbitrary. They know it is tied to ancient choices about how to divide circles. They know it marks no physical boundary and describes no natural scale. And yet, they continue to use it, not out of ignorance, but because it works. Every distance ladder still begins with parallax. Every calibration still traces back to that tiny angle. Every map of the galaxy still depends on the same geometric relationship first measured in the 19th century. The parsec is no longer just a unit. It is a fossil. A preserved imprint of the moment humanity finally cracked the problem of stellar distance. A reminder that our understanding of the universe is shaped not only by nature, but by the tools we invent to interrogate it. Other units may be more intuitive. Light years tell better stories. Kilometers fit neatly into physics. But the parsec tells a different story. It tells the story of limitation, of patience, of precision pushed beyond what seemed possible. When you hear an astronomer say a galaxy lies millions of parsecs away, you are hearing the echo of a tiny angle measured long ago. An angle smaller than vision, smaller than certainty. The universe did not choose this ruler. We did. And once chosen, it reshaped how the cosmos would be described forever. The stars are still distant, space is still vast, the night sky remains indifferent to our measurements, but every time we measure it, we do so in the shadow of that first success. The parsec is the scar left behind when humanity finally gave the universe depth